So the fitted mass to light ratios in MOND cover the right normalization for the mass to light ratio, this dependence on color, and also the amount of scatter from bandpass to bandpass. Really could not be in better agreement with that. It really could not. So, what am I supposed to say? That Milgram was wrong? Believe me, there is a huge temptation to say that, but really he's gotten many of these predictions right. So I keep trying to test this. An opportunity to do this came up in the early teens when the PANDAS survey was imaging. This is Andromeda, which is the nearest large spiral to us, which has many dwarf satellite galaxies, which are conveniently circled for you so you can see where they are. And they were discovering new ones. Some of them were already known, hence the red and the blue, but others they were discovering brand new. And with MOND, all I need is to see how bright that is, and I can predict the velocity dispersion. So let's do that. It's hard to show these data. This is the predicted velocity dispersion. That's the speeds of the stars within each one of these dwarfs. And this is for Andromeda 1, Andromeda 2. We're really good at naming things. Andromeda 3, Andromeda 4 turns out to be a background object, which MOND predicted it would be because it moved too fast. Andromeda 5, Andromeda 6, so on. So all these little dwarfs. And some of them, and people were doing the follow-up observation so fast that I couldn't really get the predictions out as fast as they were doing it. But in some cases I did. And so basically the predictions, you cannot distinguish from the observations where all those green circles are. Or the yellow circles, and there's one case that's really problematic. So you could say, okay, MOND is falsified because it gets this one case wrong. But why does it get all these others right? Can I predict this with dark matter? No, I cannot. And it's not for want of trying. I mean, it's not just that I'm looking only at MOND. I'm trying to do this from every conceivable perspective. And a number of these got right in advance. All these little gold stars, those predictions were made before the observations were made. So that is the gold standard of a priori prediction in science. Now, one of the curious things about MOND, I don't have time to go into in great detail, is the so-called external field effect. This EFB is basically, MOND depends on this absolute acceleration scale. So mostly you have to worry about the gravity of the object you're looking at. But you also have to worry about the gravity of everything else in the universe. And for some objects, that can be stronger than the internal gravity. And that's true for some of these dwarfs. So you have to worry about whether something's all by its lonesome or whether it's feeling the effects of the gravity of a nearby giant host like Andromeda. There are enough of these satellites of Andromeda that you can pick out matched pairs, galaxies that on their own would have the same predicted velocity dispersion. But one is isolated, the other is affected by the external field of Andromeda. And that means it's not as low acceleration, so there's not as much of a boost from MOND, and so the predicted velocity dispersion is lower. And you can see that difference. It's most clear in this case, but you can see it over and over again. And that's important because this external field effect is unique to MOND. It has no corresponding thing in dark matter. It's just a unique prediction of MOND. MOND predicts this, it should be there, it apparently is there, and we have no good way of explaining that in dark matter. Very recently, my colleague Ki-Hoon Choi at Sejong University in Korea found a statistical detection, not just for the little dwarfs nearby to us, but for giant galaxies at much greater distances. And the takeaway here is that the best fit for the value of the external field effect is non-zero, and it's significantly non-zero. Now, obviously, the errors are still big. We even occasionally get something negative, which is unphysical, but that's just because this is really hard and the uncertainties are big, and so things are smeared out. What really impresses me is that the peak of this is significantly non-zero. That I did not think we would be able to detect, but he worked really hard on it and achieved it. All right, so I should try to wind up a little bit. Let's go back to what Newton said, because I get complaints all the time from my colleagues. Oh, you're abandoning Newton. I would say no. What Newton said was that everything happens as if the force between two bodies is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. His famous inverse square law of gravity. And that's what this equation is. The acceleration, that is the force per unit mass, depends on the mass and the inverse square of the distance. Okay. Now, at the time, this was seen by his colleagues as a kind of magical thinking. How does one object affect another object far away? They have to be in contact in order for a force to be exerted. This is totally insane. And what are you talking about? And that's why Newton was careful to say everything happens as if. He's saying, okay, I'm not saying this is really how the world works, but it sure looks that way. And so I would make the same statement now, regardless of what's going on at a fundamental theoretical level. Mond is the effective force law in galaxies. Everything in galaxies happens as if this modification of that Milgram suggested is what's working. Now this leaves us in a terrible bind because Newton led us to Einstein, who leads us to this lambda CDM cosmology that is full of dark matter. Now Milgram wrote a theory that contains Newtons, just as Einstein did, and that explains galaxies. But these things do not go together. There is no theory that does all three. And that's what we really want. Some grander theory that encapsulates all these things, and we just don't have such a thing. And such a thing is not easy to get, right? One does not simply write down new equations of gravity. And so this is not a problem that's going to be solved overnight or really anytime soon. There has been some progress. Bekenstein made some progress, some important work recently by Skordas and Zlosnik, and others have worked on this. We're not there yet. That's good. There is still fundamental science to be done. If somebody says, oh, we've discovered everything there is to discover, that's wrong. There are fundamental problems that are still open. The bad thing, we're still sort of currently floundering around in the dark. And we argue about this a lot without a lot of noise. So I'm going to end by playing a video of my daughter and the daughter of colleague Tom Schutt, who is somebody who works on these dark matter detection experiments. And of course, we would claim not to bring our work home. But one time I did, we were at a conference in 2008, where I showed the limits from. And it happened to be my daughter's birthday. And so when I got home, having just talked to Tom and seen everything shut, my daughter's best friend, Maddie, Tom's daughter, was there with a bunch of other kids. And I walked in and said, oh, Maddie, hi, I was just working with your dad. And she looks at me and said, I thought you worked against each other. And so there ensued this argument between the girls, which Tom obsessed about reproducing. And it went something like this.
So, have you finally given into the idea that dark matter doesn't exist?
Dark matter does too exist. If dark matter didn't exist, then the eighth dimension would not fit into the quantum theory. No. We have tested it. No. The eighth dimension does not be divided by 4, the quantum theory of 8.
And that's where we're at. Thank you for your time.
Yes, thanks a lot for the wonderful talk. I want to put the problem we are in today with dark matter versus Mond in a larger historical perspective, because I think the situation is very analog and analogous to the situation 150 years ago. So I describe our situation now. Mainly, we have some motions of celestial bodies. We have a set of equations which are wonderful, well confirmed. We try to apply these equations to these motions and find, well, we don't get everything. We get a lot, but there's a discrepancy in the end. Now go back 150 years in the 1860s. There was this famous French astronomer and mathematician Le Verrin. And he, for the first time, really measured very carefully the motion of Mercury, right? And the motion of Mercury was then tried to be explained by Newtonian dynamics. And the story is this, that up to 0.7%, you could wonderfully calculate that. Very complicated calculations. It's a 200-page book because you have essentially a body problem, right? And you had to solve it without a computer, but really making approximations is very hard, but it was extremely successful, up to 0.7%. So you had to add, all the influences of the planets and blah, 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 geometrical effects. So people were somehow happy, but they want to get rid of these 0.7%. And then the first idea was in such a situation, in the same way we are today, you either change your fundamental equations or you change some of the parameters, the initial conditions, boundary conditions. Meaning, for today's situation, we leave general relativity in place and say, oh, there's additional matter, and then we get a different effect on other bodies. And in the same situation, or we say, okay, we change the equations and do Mond and stuff like that. The same was the situation in the 1860s. So most people then tried to stay conservative. They didn't doubt Newton. That was successful for 170 years or something. And then they said, okay, we've got to invent something else, namely more matter. And that was Vulcan, a little planet inside of Mercury. And they tried to find out whether that would make the changes in Mercury's orbit. It did, but it wasn't visible. It wasn't observable. Then people said, yeah, it could be planetoids, and it could be this and that, and it could be a quadrupole moment of the sun, and so on and so forth. So people stayed there on the conservative side, did not really consider deep alternatives. That only happened after Einstein started his business, which was 45 years after the discovery of the anomaly. And most people said, yes, it's a nuisance, but basically we got 99.3% of the effect. It can't be something fundamentally different. And nobody believed that until Einstein came up, and these remaining 43 arc seconds, that was the fundamental thing, that the prediction was so precise. And then everybody said, oh, that can't be an accident. So the point is what we learned from here, and I was very happy that you were so critical about those people who are too sure about, dark matter existing or whatnot. It's completely open what is going to happen. So nobody believed that 45 years until Einstein came, and this just then fell out, the precession of the perihelion of Mercury. It was a very small effect, but look, the step from Newtonian mechanics to Einstein was gigantic if you look at the difference between these two theories. So what we may expect, if we are now in a situation similar to that one, which is not sure at all, it's completely open, it may be that the step away from general relativity to something new is even much deeper than this modification that Mond introduces, and then you can play around with it. So we should be very, we should have much humility, concerning that situation. It may be many surprises around the corner, and nobody knows where we have to go. So your talk was so wonderful because I'd never seen this strong parallel with this Newton case, but I think it's very good to make us intellectually very modest. And I love that very much, your attitude in that respect in your talk.
Well, I came by it the hard way because I was one of those people who was absolutely convinced it had to be WIMPs. And I was deeply shocked when it was not my predictions or any of my immediate colleagues' predictions that came true in my data, but Milgram's. This was completely outside of my conceptual framework.
Yeah.
And I struggled hard with that for a long time. And it did require me to wrap my head around, well, geez, maybe I have been wrong at this very deep level in assuming that. And I think that's where we still are. I would say it's very hard to progress as a community until everybody has that experience, right? I've tried to make predictions for Mon in the hopes that, okay, well, it happened in my particular thing about low surface brightness galaxies. How about, you don't care about that. You care about the cosmic microwave background. Okay, well, here's what the first to second peak ratio should be. And that came true. And some people paid attention to that. But on the whole, I've noticed that community has made up an entire false narrative as to how I didn't really make that prediction. It's really, it's very hard to wrap one's head around.
Yes.